So for the next talk, we have Trusted JavaScript Language Environments with ESMeta by Jihyeok, and please give him a big hand.
Okay, so hello everyone, I'm Jihyeok Park from Korea University. So in this talk, I will introduce how to support the trusted JavaScript language environment with ESMeta, our tool. So JavaScript supports its own language specification called ECMA 262, and it is maintained by the technical committee 39 called shortly TC39. And it describes the JavaScript syntax looks like this, BNF-like form. And it describes the semantics for each syntax feature or built-in libraries using the pseudocode style algorithms. So it consists of step-by-step execution, how to execute the language features. So it means that all the JavaScript implementations, including engines in the web browser, or transpilers, including Babel or SWC, and also the research tools strictly conform to the semantics described in this specification. It means that if we have a new language feature, it means that the specification will be updated, and then all the implementation should follow up that new language features. And we need to check their conformance. So I'm sorry, so I think it is better to... Yeah, I'm sorry. So here, we need to check their conformance, but the problem is that we need to check their conformance and we need to manually update all these specification and then implementations by hand. So actually, until before 2015, it was not a big problem because this JavaScript language has rarely updated, but since 2015, it becomes really more critical problems because TC39 decided to annually update the specification. So for every year, we have a new language feature. So all the information should follow up this new update to support the new language features. So many research tools suffer from this problem. So many research tools only support this ES5.1 version because of this, they cannot follow up this new cadence annually cadence of the update. So we believe that if we can extract some mechanized specification from the language specification, then we can automate all this process. We believe that. So this I use this mechanized specification to explain to denote the executable and easily analyzable, but strictly just having the similar style written, the writing style of the specification. So this is our goal. So actually, in this talk, I will explain our journey with our framework called ESMeta. So in each step, we develop different tools, including GSet, JSTAR, and all these tools. But all these tools are included in our general framework called ESMeta. So I will first explain how to extract our mechanized specification from the language specification and how to utilize it in very different way. So let's start from the first part, see how to extract the mechanized specification. So I said that this specification describes the semantics in a pseudocode-like algorithm. So this algorithm describes the specific case of the array literal. So it has multiple steps, and it describes how to execute the array literal. But it has very similar pattern because it's pseudocode. So for example, we can define local variable using the let be blah blah, or we can call another algorithm looks like this one. And also we can invoke another syntax-directed operation for some specific abstract syntax tree. So for example, actually these element list and allegion also are parameters. You can take JavaScript syntactic component or abstract syntax tree as a value, and we can call some syntax-directed operation for that ASD by passing some additional argument. So we can do it. So this specification has specific pattern. So we want to formalize or support some meta language to capture all the patterns in the specification. So we design our own meta language called IRES. So IRES stands for Intermediate Representation for ECMAScript Specification, shortly IES. So the specification, JavaScript itself is functional, but the specification itself also functional. It supports the first-class functions or values, and also even it supports the first-class continuation. There are some specific parts support the continuation. So our meta language support their first-class functions and first-class continuation in a specific restrict form. And I explained that this is meta language for the specification. It means that we also treat the JavaScript ASTs as values. Looks like this. So this is special point. So this meta language only for the JavaScript specification. And using this meta language, we developed our first tool, Jihyeok. So it takes the language specification and automatically generates the JavaScript parser using the syntax, and then automatically compiles all the pseudocode-like algorithms into our meta language functions. So it means that it is actually interpreter. We can execute JavaScript programs using the mechanized specification. If we have meta language interpreter, then we can execute any JavaScript programs. And the core part is this one, and to support the compilation, we manually define more than 100 compilers. So for example, we can compile this single step into our meta language instruction looks like this using some specific compilers. So this is how to extract the mechanized specification from the original language specification. So now we have mechanized specification from the original specification. Now we can execute JavaScript program on our mechanized spec, or actually we can mechanically handle the semantics using our extracted mechanized spec. So our first application of that mechanized specification, we want to detect some errors in the specification by analyzing the specification. So we want to design the type analysis for specification. So this was our first application. So I will show you what happens if we perform the type analysis on the specification. So this is the semantics for built-in library math.round. So it takes any JavaScript value, so the parameter x, the type is any JavaScript value, string type, boolean type, number type, object type, and so on. But after calling the algorithm to number, it returns not only number JavaScript value, but also JavaScript exception. So JavaScript exceptions are also values in the specification, so it returns both either of one of them. But this question mark operator filters out the exception values. It means that if the return value of the two number is exception, it directly returns to the caller. So now we have a number type. So the variable, local variable n, the type is number. But let's look at the step 3 and 4. In this step, this algorithm compares the variable x with mathematical values 0.5 or 0, but it is the specification error because in the specification there is no meaning when comparing the non-numeric values. So for example, if we pass the Boolean value to the math.round, then this Boolean value will be passed to that parameter x, and in this algorithm tries to compare the Boolean value with the mathematical value. So there is no meaning. So this is obvious specification error. But actually, this is not an official release version because ECMA 262 is maintained as an open source repository in a GitHub. So this is internal version. So at this point, in this internal version, it happens. But before releasing the actual official version, it was fixed. Looks like this, using n instead of x. Now we have the correct semantics, even when it takes Boolean values. It looks like this. So if we perform type analysis, we can detect these kinds of bugs and specification errors. So we developed a tool called JStar, that's type analyzer. We successfully detect 93 type errors with 59.2% precision. And among them, 15 bugs are newly detected by our tool. And after developing the first tool, we realized that we needed some more advanced type checking to reduce some false alarms because the precision is 59%. And for example, this is ongoing work. So here, this is an example of our motivation. So let's look at this part. And first, pattern can get any JavaScript value. But here, the get algorithm requires object type. So it does not match. So it throws a type error. But actually, these two alarms are false alarms. So to remove these false alarms, we need more information during the type analysis. So here, actually, each regexp algorithm return type is normal Boolean type, but we want to infer another type constraint if each regexp returns normal true type, then the argument pattern should be object type. If we can infer that type constraint, we can utilize this information. For example, we can propagate this information to this pattern. Oh, I think there is problem. Sorry. So we can move to like this. So here, pattern is regext is Boolean type, but if each value is true, then we know that the pattern is always object. If we apply this part into here, then at this point, we know that the pattern is always object type. Then we can remove these false alarms. So we want to do it. So this is ongoing work to reduce the false alarms in the type analysis for specification. So this was the first application. Now let's move on to the second application. Now we want to utilize mechanical specification to check the complements between the specification and implementation. So these two things should come from each other, but how to check it? So typically we need to use developers utilize the conformance test, and T39 supports the official test suite called the test262. So a single conformance test is just JavaScript program, but it consists of two different parts, program part and assertion part. For example, this is an example. So it says that 4 plus 2n program should throw type error according to the semantics of this specification. So the engine developers can execute this test suite to check their conformance in their implementation. But the problem is that this is manually maintained. So it means that we do not know that this covers all the semantics in the specification, or is it really conform to the semantics in the specification or not? So to resolve this problem, we want to automatically synthesize conformance tests from our metacanalized specification. So we utilize the mutation-based fuzzing. So first, we construct the initial program pool using the syntax described in the specification, and then we iteratively mutate the programs looks like this based on the specification coverage. So it is coverage-guided fuzzing. So our goal is to increase the coverage in the specification. So I will show you the concrete example in the next slide. And then finally, after convergence of the spec coverage, then this tool automatically injects assertions that looks like this. But these assertions comes from the final state. So I said that this is interpreter. So if we execute these generated program on our mechanical specification, we can get expected final state for each program. Then from that expected final state, we automatically infer the assertions for each program. We can assign the assertions looks like this. And specification coverage means that it looks like that we have a program pool. Then if we have this program, we can cover that part. If we have this one, we can cover this one. We can have this one, and we can cover this one. But actually, we think that it is not enough. Why? Because this is a single algorithm and different edge cases, but multiple different language features may sometimes share the same algorithm as a helper functions. For example, this algorithm, language feature addition, subtraction, and multiplication, their semantics are defined by with this same algorithm. So it is not enough. We think we need to split. We need to cover all the edge cases for each language feature looks like this. So we split the context based on the innermost language feature, addition, subtraction, multiplication, and we can cover all the edge cases for each language feature. So we call this is feature sensitive coverage, and we extended this concept, and we can increase the diversity of the program to detect many different edge cases in the real world implementation. So using this idea, our tool, we developed a tool named Jest, and we detected real world engine bugs, 42 engine bugs, and 94 different transpiler bugs in the real world implementations. So this was the second application. But after synthesizing these programs and checking the coverage of the test conference, we realized that this synthesized program or filtered test programs are really helpful to advancing the understanding of the specification. So we developed another tool, JSpec, some specification visualizer. So this visualizer consists of two different parts. For each program point, we showed what is the minimal program, synthesize the minimal program for each program point, and which tests we need to run to test that program part. And then for each program, we can actually run online to step-by-step execution. Using the step-by-step execution, we can see the internal state or what happens in the state in the spec, forward or backward way. So I will briefly show you our tool. So our tool is released in the Chrome extension. If you install our Chrome extension, this is actual online version of the official language specification. After installing the Chrome extension, you can see the right side panel. And if you click each program point looks like this, then you can see the different programs, the minimal program, and which tests, specific tests we need to run to test each program part. Looks like this. And if you click the run on double debugger, looks like this. This is the online version double debugger. And this is the synthesized program. And if you click the resume button, looks like this, then it directly jumps into the what we interested part. Then you can see what happens in the specification, what happens in the JavaScript, and you can go forward or backward. For example, back over, or step. Looks like this. You can do it in front, forward, or backward. You can do step-by-step execution. Yeah, so this is another tool to advancing the understanding of the specification. And the last application is about the derivation of the implementation. So we want to not only checking the components between already existing implementation with the specification, but we also derive implementation directly from the Mechan specification. So our first target was static analyzer. Then how to do it? So we have the spec, and we want to analyze this program. How to do it? So after applying our approach, we can automatically extract the Mechan specification looks like this. And then I said that this is the JavaScript interpreter written in our meta language. Then if we have meta language analyzer, then we can analyze this Mechan specification, and we get the analysis result of the specification. But in other words, we can say that that analysis result just includes all the possible behaviors of the interpreter. But if we restrict the initial state based on this program, then that analysis result includes all the possible behaviors of the interpreter when it takes this program P1. It means that this analysis result represents all the possible behaviors of P1. So this is the concept of meta-level static analysis using the definition of interpreter and the given program. So using this, I will skip the details. So this is the result. After deriving the JavaScript static analyzer from the latest spec, so our empirical study shows we can derive always sound analyzer for it covers all the modern features of the JavaScript, but manually written, maintained JavaScript analyzer cannot handle soundly support the modern language features here. But actually, this is not practical because we need to perform meta-level stack analysis for all the parts. We build all this JavaScript stack analyzer from the scratch, but I think it is not the ultimate goal. So the appropriate way to use this one, it is better to automatically derive some specific part, not yet covered part for existing analyzer. So we want to derive the specific part, the specific component of the stack analyzer, or we also want to derive this transpilation rule or data flow rules from this backline specification by analyzing them. This is our next goal, to support the to derive other language implementations. So I explained how to extract the backline specification and how to use it. If you're interested in our tool, so please visit this GitHub link. So it is the open source. So that's all for this talk, and thank you for listening. Yeah.
So the JavaScript specification has occurrences of implementation-defined behavior and permits implementation approximations for certain mathematical operations. How does that affect your analysis and your test generation and stuff?
Yeah, so we realized that the JavaScript specification has implementation of host-defined features, but we assume that at this point we implement it in a single specific implementation. We assume that deterministic version of our implementation for that implementation version, dependent or host-defined semantics, but we want to support the implementation dependent or host-defined semantics in the future, but not yet. So at this point, we only implement in a specific way for all the features. Yeah, that's all. Thank you.
Hi, thanks for the talk. There was some really cool demos. So I was wondering about this. You showed this where you clicked on the clause in the specification and it showed the test cases.
Yeah.
How does that work? Do you have annotations in the tests, or does it automatically find this? How is this linking done?
So actually, this is pre-calculated annotation. So before releasing our tool, so we already execute all the tests, and then there is annotation. So this test covers this part, this test covers this part. So we filter based on that annotations. So yeah.
Okay, so it's automatically computed, not manually annotated.
Not offline annotation.
Right, but automatic.
Yeah.
Okay, cool, thanks.
I have a question about the JSTAR. Since that you are writing a type checker to find the error in the spec, and I want to ask that if you want to generalize your approach for different language, do you have to implement different type checkers? Actually, it's two questions. There are two questions. First one is that can your approach be generalized to different languages? And second question is that do we have to write different type checker for different language?
Yeah, I think the two questions are really similar. I think, yeah. So this type checker only for JavaScript language specification. I think for different language specification, I believe that it is better to design different type checker for different language specification because they have different style and different problems and different checking requirements to check to detect some bugs in the specification. So yeah, I think this JSTAR only for the JavaScript language specification.
Oh. It is very impressive that how you cover whole ecosystem of spec definition and implementation, not just focusing on specific topic. And my question is, Can we see the JSTAR statistics slide?
JSTAR.
About 14 bucks.
Oh, about 14 bucks. Okay, about. You mean this one?
Yeah. I wonder what was happening in 2015, September 22.
So. Okay, so actually, I said that the ES6 version is released as they started from the annual release. So actually, ES6 in this is a really big change. So actually, also the specification style was really big changed from the ES6 since 2015. So we cannot cover the old version. We cannot cover legacy versions of the specification. So only covers the at this point. So this is start of the new style of the specification. At the first time it has the that kinds of bugs. Yeah.
So the bug was not by one criminal or
one criminal, not one criminal. So it just started from the initial version of the new style of the specification. But these are not critical. But yeah.
So thank you for the great questions, and let's give him a big hand.
Okay. Thank you.